If you've got wafer tweezers, probably best to try and use those to handle wafers, or a vacuum wand or something like that. Or otherwise just hold them like at the edges. Avoid transferring anything onto the bonding surfaces. Okay. So now I'm going to load my bonding wafers. No, this will be okay for an anodic bond, just to hold by the edge. So, glass on the upper wafer. At the moment, I have a graphite platen installed here. This is best for anodic bonding. You also have two other platens can go on the upper here, which are a tungsten for chip bonding. Yeah, tungsten for chip bonding, so they're here. So this is a normal tungsten platen for wafer bonding.
Very heavy.
And then in here, there's another tungsten platen for chip bonding, which has a longer slot in here and a little recess in the middle for holding a chip. And then you also have a separate wafer clamp assembly for clamping the chip. I'll demonstrate all that later when we do some hardware work. So.
Packaging chips or universities. Yep.
Okay, so that one's secured in there. Just trying to align the flat of the wafer with the flat on the platen.
Would you mind showing the clamping again, because I missed it?
Sure, no problem. Okay, so all we do is push the wafer up against these two little screws. Rotate it so the flat is aligned with the marker. At the moment, the nose of this clamp is underneath the wafer.
Yeah.
So I'm just going to retract that, push the wafer down on that corner, and then that nose can make contact. I already set this up yesterday, so we have on this assembly a thumb wheel there to control the height of the nose and a little spring adjuster here to adjust the clamping force. I've set those up already, but I will demonstrate that later to you how we do that setup. That's the kind of thing that you set it up once and then leave it.
You show them the pin. I think they were confused on the center pin. You can see it now.
Yeah. So I don't know if you can see just through the middle of the platen there, there's the little ceramic pin tip. So I haven't set that up at the moment. Well, I mean, I did set it up yesterday, but with a tungsten platen, and I've now changed it to a graphite platen, so I need to set it up again. But the idea is when it's screwed in, that protrudes by a fixed amount of, say, 100 microns, and that can then put a little bow into the wafer. Don't really need it for this purpose at the moment. So.
Okay, this is anodic bonding is the graphite, and then the heavy one is for compression, high force, so compression bonding.
So a direct bond, you don't actually need to apply very much force, only say 500 newtons. You can do that with a graphite platen in as well. For thermocompression bonding or metal to metal eutectic bonding or glass frit solder bonding, these are things where you need higher forces, you need to use the tungsten platen. And obviously for chips, use the special chip platen.
The graphite chunk will break if you push too hard. So if you have a high force pushing, you need to change to the.
You can. You can, yes, you can.
Okay.
So basically, you can just put tungsten and like keep it there for everything.
Yes, but if you do anodic bonding with tungsten platen, you'll get sodium plating. So
Yeah,
in these wafers there's sodium doping, and that will come up and it will plate out on the platen and it makes a mess of it. So the graphite platen is good for this because it just kind of absorbs that plating. In theory you can do the tungsten platen on, you may or may not be lucky and be able to wash it off with deionized water, but probably you're going to stain the platen. It won't affect the process, it will still work, but it just kind of looks a bit messy.
I see.
So that's why we recommend to use the graphite platen. Also, you have these graphite discs. So if you don't need to do alignment, you can just stack your silicon wafer, glass wafer, put one of these on top of it, and then use the tungsten platen as normal with one of these in. Then the plating will go into one of these, which are basically disposable.
Okay, and they have a hole in it, right?
Yes, they have holes in it, so you can do alignment. So you can also use these for force uniformity, to improve force uniformity. So if you need to have an even force across your bond, right across the bond, you can put one of these on the lower platen, put your wafers on top of it, and then when you bring the force up, this helps to sort of spread out the force. So that's another use for these, and that's why there's a hole in them for doing alignment if you're using it for force uniformity, as opposed for anodic bonding to trap sodium plating. Now, when we set this wafer clamp up and we select these screws, we have different sizes of these screws, so the screw heads are different thicknesses depending on different wafers. So for anodic bonding, it's critical that the screw head is below the surface of the wafer by about 100 microns. So my wafers are 500 microns thick and the screw heads are 400 microns thick. If the screw heads are above the wafer, firstly it won't clamp properly, and secondly it will make contact with the lower wafer and short the bonding voltage. So it's critical that we have a gap. That is what I was just checking with my thumb to make sure that there's a distinguishable gap, which there is, so I think we're good to go. Okay. Right, so I'm going to start a new run. Okay, so for doing my anodic bond, the first stage of the process is to pump down the chamber and get it under vacuum. So to do that, I need to open the isolation valve, which exposes the chamber to the pump, and switch the pump on. And now we wait. So in a minute, you're going to hear a click, and then you're going to hear that pump start to work. I'll explain to you what's happening there when it does it, so you can listen out for it now. There we go. So what's happening there is when you flick this toggle switch, that pump will come on immediately, it will evacuate the plastic tube, evacuate the backing line. Then there's an interrupter valve between the backing line and the turbo. That's on a time delay for about between 15 and 25 seconds. So after a while that opens, and then the turbo will start actually spinning up and pumping out the chamber. So the tick that you heard was the safety valve opening, and the pump noise that you can hear is it starting to pull the air out of the chamber. The reason that safety valve is there is so that in the event of a power failure, the turbo pump doesn't get vented through the backing line. So that will immediately close to protect the turbo pump.
You said there will be a blue line showing the pressure, right? And then the red will go and match.
If we are using controlled pressure, then yes. At the moment I'm not using that, I'm just pumping out. So I'm not pumping to any, I haven't actually requested any value here with the pressure control. So if I turn that on, then this grey needle will turn blue, and the needle will move to the position of the pressure that I've requested. But for now, I don't care what the pressure is, I just want vacuum.
So if from the configuration it shows millitor instead of millibar, this,
Yeah.
all this interface will change.
Yep. Hopefully it will. Hopefully it will. I've never actually tried it, so hopefully it works. I'm used to millibar on this machine. I was used to millitor at my previous company, the other machines I used to work on, but on this bonder I'm used to millibar. So at the moment I'm just separating the wafers. What I'm going to do, once I've got the chamber under vacuum, I'm going to apply 800 volts, make sure that there's no problem with the voltage system, make sure there's nothing shorting out. I want to do that before I start heating up, because if I heat it to 370 degrees and then I find there's a problem, I've got to wait for it to cool down before I can rectify the problem, and like it just wastes time. So I always do that little check before I actually go for the bond.
So first try the voltage, everything is okay.
Yeah, that's advisable. So yeah, I get a nice separation between them, apply some voltage to the upper platen, make sure it works. There is always a chance that if the wafer clamp isn't set correctly, when you apply the voltage it will work. Then when you bring the platens into contact at temperature and then switch the voltage on, it might get a short circuit. It's probably due to the wafer clamp nose height. And then that's annoying. If that happens, you have to wait for it to cool down and start again. So hopefully my setup is okay. It's always a slightly tense moment. So when you've got the platens, when you've got the wafers heated up, you've brought them into contact, you've applied a clamping force between them. When you actually switch the power on, it's always a bit of a fingers crossed, hope it works kind of moment. So what we find with this, pumping down to 0 takes quite a long time, and then once it gets below 0, the pressure falls very rapidly, down to about 10 to the minus 4, 10 to the minus 5 millibar.
clear these airways and
The the purpose of that pump is to assist the turbo pump. So the turbo pump won't be able, it doesn't really have like enough power to evacuate the chamber by itself. It won't be able to accelerate while there's a big gas load in the chamber.
You first start by pumping to a certain pressure, then the turbo pump will start.
Well, the turbo pump just kind of regulates its own speed depending on what the gas load is there. So to start with, there's a whole chamber full of gas that has to be got rid of. That gas is basically cleared by this pump. That pump can get down to about 10 millibar, and from then the turbo will be able to accelerate and kind of takes over and gives like the high vacuum performance. So we can monitor the turbo speed here with at nearly 1000 hertz. Without any assistance from the backing pump, it can get to a maximum of about 128 hertz. That's all it can do. It just starts struggling. It can't cope with the amount of gas that's in there. So the turbo pump needs to have a pretty good vacuum already there before it can really accelerate and take control. And this is also why there are many features, and we go to great lengths to avoid venting the turbo pump. So when it's spinning at full speed, you don't want to introduce gas into the chamber because it will crash it. It will stall basically, and it doesn't like that. It will ruin the bearing if you do it enough times. So there are various valves and interlocks and safety conditions to prevent that from happening, to protect the turbo pump, because we don't want to screw it up because it's very expensive. Right, so we are under vacuum now. 10 to the minus 4, full turbo speed. I'm just going to apply my bonding voltage. So for a 4-inch wafer, typical parameters, 800 volts, 4 milliamps. That's good. So the voltage is stable, it's working. Well, it's working with the wafers in separation at any rate. So now I'm going to heat it up, bring the wafers into contact, and then apply that bonding voltage, and we'll actually start generating the bond if nothing goes wrong.
So you just use the HV supply right now on and off just to see that everything is good, right?
Yes, exactly.
Okay. And the 4 milliamps is a limit. After that, it shuts down, or what?
It won't shut down. At the moment, the 4 milliamps is really meaningless because all I'm doing is applying a voltage. There's no current actually flowing.
Yeah.
So when I've got the wafers heated up and in contact, there will be a current flow.
So once it drops to 4, it stops?
No, what will happen is that the current flow will rise up to 4, and then it will limit it there. So to start off with, it's only going to require about 100 volts to achieve 4 milliamp current flow. As the bond interface starts to develop, it will require ever higher and higher voltages to maintain 4 milliamp current flow. And then eventually what happens is we'll reach 800 volts, and then voltage limitation will kick in, and then the current will start to decay. So what we're going to see is we're going to see a red line, which is the current at 4 milliamps, and we're going to see the white line ramp up until it reaches 800 volts. And then we're going to see a crossover point, so the white line will become a flat line at 800 volts, and the red line will start to exponentially decay. That's what we're going to see if the bond works. So I'm going to set up this graph now. I'll set that to 900, so we can just so that we can see the voltage. It won't be like obscured at the top of the graph. Likewise with that.
But what happens if you increase the current, let's say, to 10 milliamps? Would it go to 10 milliamps?
It would maintain the current at 10 milliamps. So that what would happen is the bond would form more quickly, but in a less controlled fashion. So you could potentially start heating the wafers or stress the wafers or crack them, where you wouldn't get a uniform bond interface. So you have a more rapid bond, but it's kind of less controlled if you did that. Similarly, you could have a lower current limit, you'd have a more controlled bond, but it would take longer. So we've kind of optimized it, found that about 4 milliamps for a 4-inch wafer is about right. In total, the bond should take about 15 minutes to develop.
We use like a hot plate and some weights. We put 600 volts on.
Yeah. Yeah. So I mean, I've seen a homemade bonder in Southampton University do a similar sort of thing. They just applied 1,000 volts to it. Fireworks goes off, it sparks. It looks like there's sort of great plasma forms inside it and all sorts of. But it just looks like the whole thing's on fire, and it looks highly dangerous, to be honest. So this is nice and controlled and safe, this bonder. So if we didn't have any current limitation, what would actually happen is you just see a current ramp up, a current spike, then that would decay away.
Yeah.
So what we're doing is we're just chopping off the top of that spike. So we're going to ramp it up to our limit, hold it there, wait for the voltage to catch up, and then it will decay. So we're just going to cut the uncontrolled top off of that spike.
So, and you were also showing that it stops over here. It's something like 0.4 milliamps.
Yes, yeah. That is a little bit of a kind of subjective figure that we've just kind of pulled out of the air. So in theory, what we'd actually need is, if you allowed it to develop in an uncontrolled way, you'd be 10% of the peak. So we've just sort of taken the same 10% but of our limitation rather than off the peak. So if it's taking too long to get to 0.4 and you're not really getting much charge transfer happening, you can just say, well, stop it now.
I see. Yeah.
This is kind of an arbitrary parameter that we've come up with.
No more bonds are happening.
Yeah.
Yeah. Once you've got no charge being transferred, the bond is
No current.
formed.
Basically.
Yeah. So we just have this